record this.
Okay, so you see the presentation mode, right?
Right.
Okay, so as Madi already mentioned, I'm going to talk about the autonomic cloud computing. There are some challenges and proposals on this topic because there are a few enhancements that the paper will talk about. So we'll see that. So this paper identifies some of the open issues on the automatic resource, some of the early steps and the proposals for the management techniques of what we have been seeing on the cloud computing. We have seen a lot of layers, a lot of software as a service, platform as a service, but there are a few parts of those steps that can be automated and with the objective of reducing the consume energy, the power that it is being used by the virtual machines, the network consume. So we'll see some of the examples proposed here and some of the through benefits that are expected in the future. So for example, the paper starts with two different definitions from cloud computing, pretty similar to what we have been seeing with previous papers. But just as a reference, it's just the users consuming something from the cloud, mostly from the, let's say, as example, the REST operations, and by dynamically getting information, services, resources without noticing if it is getting scaled or not. So that happens behind the scenes. So let's see. And currently, there is a pay-as-you-go model business where companies have been moving from internal private cloud to hybrid and even hosted private cloud, in which the provider brings this service for the customer stop worrying about the configuration and some more complex work for they being able to only work on the application as a whole instead of having like the full operation team. So in this kind of environments, there are like a specific automation tasks for each customer and some general ones, as we'll see in the next slides. And some example of the big companies working on this are these, Hewlett-Packard, IBM, Amazon. So this have started working with this automated process to enhance the user experience and at the same time to reduce the cost for them because they have like a huge amount of money inverted in the servers and all the clusters that they have. So at the time that they can improve the performance and the cost of all the resources, the customer will also get some of that same benefit. So as we have seen in previous presentations, the cloud computing involves a lot of layers, a lot of services, and a lot of challenges. So one of these are the network, the storage, performance, security. So there are some of these challenges that are trying to get tackled with the automated process. So one example is the quality of service, trying to get all of these, like the usability, the availability, performance, and stability in the whole systems. But it is not only that part. There are multiple sections on all these different layers, like mentioned the energy efficiency. We've seen like how having a huge amount of resources just on idle state won't be helpful either for the environment or the company, or even the customer paying the amount of money for those. So the idea here is to find some of these process and find some patterns to identify where the system can start saving some of these resources. Another important one is the security, where, for example, the denial of service and all the login operation, something that it is pretty common to different customers, can create some stress on the servers, start consuming some energy, and maybe the application starts creating more instances, but not all of them are required. But because you are receiving multiple requests, that's how the system start creating more and more virtual machines. But in the future, those won't be necessary, and you are just consuming yourself. So some of these scenarios are the ones that are being trained to get into automated systems. Here are some examples for what is considered an automatic system: for self-regulating, self-healing, self-protecting, and self-improving. So basically here, um, it is trying to match the full demand on the services and the servers with the supply that you have to give to all the customers the best experience at the time that you don't force or all your systems to be on the edge of the process, or the like having a ton of work to handle at the same time. So just like the required minimum. So one example of this is the Amazon Elastic MapReduce, um, but it is not like the best approach or the most mature that it can be. It is just an example of how things are working on for the automated process and how those can get to be in future as soon as this gets more implemented and with better improvements. So we have this example with something that we have seen in previous presentations. We have seen what is a system as a service, the application portal, well, all the customer being the application, the server receiving some information in real time, like for example, for healthcare. And the proposal here on the autonomic management system stays on the second layer. As you can see, there is the security and attack detection, the quality of service, the overall cost, energy efficiency, and the data location. So here is where the workflow can be reduced and the stress for the server try to be reduced as well by keeping the same quality of service and the reduce of energy, not going to the limit. And this is just to try to avoid any consequence or bad consequence to pass to the last layer, where is all the servers on the backend relies. So for example, we can see we have here the application scheduler on the second layer. So basically here is like, it depends on trying to identify some patterns or multiple routines running at some specific time. And depending on that, it will decide um, when to turn on or turn off some of the services, the virtual machines, and to reduce the stress on your servers. Like for example, if it is required to relieve the network usage, it will start turning off some of these, also for storage. So depending on that, the scheduler will start killing or starting some of the new processes, if some resources are needed or if it needs to release them for other critical processes. So here is the energy efficient scheduler, which also relies here on the second layer for the energy efficiency. This one is because it is pretty difficult to automate, considering both goals, like the carbon footprint and the cost of the management for all the servers. In one hand, we try to reduce the amount of energy that we will be using for all our processes. And by the other hand, we will be trying to reduce the total cost of the operation. So because of that, we have to find like the critical point where we satisfy both. But at the end of the day, most of the times we need to sacrifice one of those, either the cost of all the operation or the footprint that we will be causing to the environment. That's one of the difficult parts to achieve here. And the dynamic resource provisioning algorithm, which is also mentioned. This is because we have some contracts that we need to rely on and will be like the source of truth of those kind of decisions. And at the same time, we have like these history values from the company and the customers. From there, the algorithm will be able to learn and identify some processes that can be enhanced. And in that way, we'll try to identify for future what can be like the best approach to generate the virtual machines and all the storage that will be required at the same as some other resources like the network to be used for every one of those calls to the server. And based on the user history, it will try to rely on the prediction to reduce either the footprint or the cost. So the dynamic resource allocation is also similar, but here based on the history from the recent calls, it will decide if expand or shrink the resources that it will be handled by to the customer making all these calls, and calling some of the scheduler to kill some of the not more required virtual machines to release some of the virtual machines that are on the idle state, for example. If those are no longer required or the algorithm detects that in the short future those won't be needed, it starts to kill those, maybe for other services to start taking them. But the importance here is when it will try to anticipate to increase or reduce the computed power for all the requests. So this is based on the prediction for the resource selection. So based on the data generated, the algorithm will try to identify what kind of machine to create to process all the requests. So here it can be that if some huge amount of storage or network is allocated for that specific call, then that will be suffice or might not be enough to the service to respond correctly. So based on that critical decision, that can be a cost reduction or cost more if the decision was made wrong. So for example, if there is an easy request to handle here, and maybe just needing some megabytes to handle or to process, and maybe a small or low storage is required with memory, low bandwidth. But if by the other hand, the request is a huge one, a big machine with huge resources will be needed to be created or to be split into multiple ones to handle that one. In that way, it will be easier for the server to handle that. So that's where the algorithm will need to decide for which kind of response to generate to tackle the request. And again, that considering the energy efficiency on the server and the cost amount for the customer. So again, to mention the security and attack detection, there are some patterns that the algorithm will be trained to identify. As one example, for the recently launch of a video game called Overwatch 2, there were some issues because they received some DDoS attack, which is the distributed denial of service. And that's because at the time of the login for multiple users or players, it started to create multiple instances to receive all these requests, and that created a huge stress on the server side, creating like the bottleneck for all the users being able to pass to the main game. That causing the issue of none of them was able to play the new game and affecting the reputation of the company. So based on these automated processes, the algorithm should be able to identify which of the requests are from real people, from real devices, which has like have been previously identified correctly to get access to the system, and those that are only there to break the security and go to the next layer as we saw here. Which we will compromise all the system. But for that, the algorithm needs to be trained and understand all the common benefits and attributes from the request coming from authenticated players and not from multiple bots. So in the paper, there's also one real life example of this improvement happening. Like, for example, in Singapore, there is this challenge to identify some data coming from the mosquito. And there are different data that will be considered, for example, the weather, the geopopulation, and some of the previous records. After having that data collected, it goes to the analytic models for processing, and then it happens the visualization. So let's see. Here the issue is that there are some dates on the year that for some reason the mosquito data starts to increase. So if the process was um, enough with some small capacity to handle all the data, it happens similar to to what we saw here with the pandemic situation, that hospitals start receiving more and more information. So the system needs to handle more and more data, and the original given resources are no longer sufficient to handle more requests and more data. So the system needs to increase capacity to keep researching in real time and send all the reports for the process to start and giving more real data as the output. So if it starts as megabyte or kilobyte, it can um, increase to the gigabyte or terabyte size. And in that time, also there are multiple records being created. So the system needs to come from a small one to a big one, or creating the multiple instances for being able to handle all the requests and process all the information in a short period of time. For example, if it creates one report at some point of the day, being able to have the report on time, even if all the data has increased by a huge amount of it. So we have this as example of how the inputs goes. And in here we start in A, and then all the B's will be splitting all the information, and then a third iteration, which starts on C, and then it finish on the H. And after that, the model starts with a loop coming from H back to the start of A, which is this arrow from the left. So the autonomic algorithm will detect some of this behavior and will be try to, with each iteration, save some resources, save some storage and processing power to reduce the cost and the energy cost to to give the same result with less resources based on the pattern created here. So in here, the author mentioned that based on some of the pattern and dependencies created, which each time that the process gets run, um, the system will get more aware of on how to increase or reduce the resources, or to call the scheduler to kill some of the instances or create a new ones for being able to handle all the operations. And here the goal is being able to do this same process with less resources, or to consume less network, less storage, like trying to use the minimum possible to reduce the all cost of the server side. So this was a short paper, around 6 to 8 pages. Hope you liked it. And some of the takeaway points are like the security, the avoiding wastage of energy, and some of the optimization on the fine touches for this algorithm. And it is something that is still in progress, and probably next in the future we will see more of the benefits and some of more complex examples of how this is working on the cloud computing. But right now it's pretty difficult to decide between handle the security and the customer experience against trying to save all the possible energy at the same time. So that's it. I don't know if there are any questions.
Okay, Christian, thank you for your presentation. And so, I mean, by this takeaway point, I mean, I just asked this, then I don't know who's going to manage the discussion. Is, let's see, Gautier. No, see, yeah, no, Hugo Rodriguez. But here, by takeaway point, security, avoiding wastage of energy, optimization through finding dependencies and pattern, I didn't totally get. I mean, so you're presenting it like a trade-off, right? That did I understand it correctly?
Not specifically a trade-off, but at some point right now, yeah, you need to make a decision at some point, because not always it is you will have like the both of them on your side. If you're trying to save some energy and keep like the good customer experience at the same time. Not always, but sometimes.
Can I say something that took my attention? Hello?
Yeah. Yeah, we can hear you, Juan.
Oh yeah. Yes, I was thinking about how you can balance between having a good customer experience as well, save energy. I think it's a very difficult thing to do. Particularly in this paper, I think there was not some kind of metrics, right? Because in my presentation, I was speaking about sustainable CDCs, how they measure it. So here we do not see something similar. So I think with the time it will be, it will increase the saving energy as well, maintain customer experience, especially in this kind of environments that everything is electronic and you need to have a lot of power to maintain some kind of or a specific performance.
Yeah,
to think about.
For example, the way I see it, it's like similar to when you are driving, and if you are comfortable at some speed and you can turn on the AC at some speed, it will be like you are on on a good velocity, and the AC consumes lesser than if you go with the full windows down. So it's like the breaking point for you, where you are starting to save some fuel against going like full speed of your car, consuming more power. So the automatic process here is trying to find that balance.
Yeah, it's possible to think about it in that way. It's just something that came into my mind.
Yeah, Pedro, you want to say something?
Me?
Yeah, I saw you unmute. I thought you want to say something.
No, actually, which was the original question? I got lost.
It was not a question, it was like something that just a comment about how to balance the energy efficiency and also keep a good performance or something that is it is acceptable for the business.
I think the paper is more into the wasting energy is not using resources. It's not more like we're going to save a lot of energy just implementing this. It's just a little more like in the idea, if we are not using resources, we are saving energy, right? So like, for example, the security example that they are portraying there, the one that they say that they are going to, they have like this algorithm that is checking patterns, so they can actually recognize when this is an DDoS attack or it's just a lot of traffic from real clients, for example. So they say that, well, we are not wasting money using more resources, and also we are saving energy because we are not using those resources, right? I think it's more into like that point that they can like some kind of garbage collector. So if they are not using some resources, they can turn off those resources, and in that way they are saving energy.
Yeah, I agree with that. I guess this paper is talks more about efficiency and service level agreements. As per I understand, this thing or this stuff about saving energy. The main point or the end or at the end, the purpose is to accomplish a service level agreement and try to not go further in cost of the use of the infrastructure.
Okay, another basically point, Christian, if you go back to slide 21, 22, just before this, yeah, this one. I mean, general comments about all the pictures you include. I mean, when you're putting a picture, you have to explain them very clearly. So I got lost in some of the pictures. I had to go and read the title of the picture to find out what's going on basically with the figure that I'm seeing on the screen. So for example, the next one, still I didn't get the next one very well. Can you go to the next?
This one?
Yeah, this one.
Okay, so let me go back to this one. This is because at the start with this Mosquitto implementation, they start here on the A, and then it creates like multiple requests in the Bs, right? And at the end on the H, at the end of the iterations, it creates a loop back to the A. And for every one of those iterations, and the algorithm will try to by finding the pattern to reduce the processing time and the resources given for every iteration. So with every iteration, it will start to reduce the power or consume.
So what is that blue and red things that I'm seeing?
Oh, sorry. I said like the power consumption for all these instances.
Mm-hmm. I mean, does the blue represent something, red represent another things, or?
Okay. I see it like the cost across the time for every iteration, but yeah.
Okay. Yeah. So that was the point. Just to try to explain the figures, because sometimes you see the figure and you get lost. But what is exactly I'm seeing in the screen? I don't know if there is any other question from anyone.
Yeah, I don't know if any of you at your workplace already have in place or know about a technology that goes all the way into this extra effort. I mean, we are in this paper, we're already talking like an abstraction layer that is over the one that we're used to with PaaS and SaaS and whatever, because now we could, with these autonomic type of systems, if we could get them working, we could get up to a point in which we only say, hey, just guarantee these 3 quality of systems parameters and do your mess, right? I mean, we wouldn't need to worry about anything else. We wouldn't need to worry to specify how many replicas, or just check the health of each of the systems, or open an endpoint to check how we should scale. I mean, I don't know if you guys know of any technology that it is already in the market doing all these for us. I mean, and in preference that is over a cloud.
Apparently no.
We're lost, like completely lost.
Yeah, apparently it doesn't exist, or at least we are not aware of.
Yeah, I mean, I don't know. Sorry?
Well, in fact, there are some, well, I understand the paper as a kind of a portal where you can control all the items or all the computers, and you can get analytics. So you can find out if someone or something is failing, and try to try in advance, or having advanced information that ensure you can fix the problem. But about your question, most of the infrastructure companies most of the companies that sell infrastructure, may mean servers, switches, and everything, currently, or at least the most important ones, sell with the equipments, the licenses to have these kind of portals in the cloud, in order to get analytics, or maybe to work with the provisioning, and all sorts of security stuff. For just to name some of the brands, Cisco has this stuff. They sell all their accessories, I mean, access points and everything, routers, and they have this license in order you can follow up the infrastructure development, or how is it working. Also, what else? I guess Fortinet, they also have something called FortiGate. It's a portal where you can see or check how the infrastructure is working, I guess. And also in this paper, it talks a lot of Amazon. Seems they are developing their own portal or their own software in order to keep track about the infrastructure performing. I guess that's kind of difficult that having Amazon working also in develop all this software in order to have a control of their infrastructure. I guess, well, I would say someone else, other parties working for them, but as seen in the paper, it looks like Amazon is developing it. Well, in fact, it's the paper don't says who is developing this tool in order to control all the servers and everything in their data centers. And well, just to conclude, and as I said, there are software already developed and also sold by a lot of brands in order to do this automatization among the data centers infrastructure.
Okay. Thank you, Gautier.
Thank you, Gautier. Pedro, you wanted to add something? Or? Okay.
No, why? I was
what-
just coughing.
Yeah, no, I saw that you unmuted, so it's not that I want to bother you. I saw you were unmuted. I thought you want to say something. That's why you unmuted. So
Actually, I was mute.
No, you did it. You did unmute for the first 5 seconds, then you mute again. So I thought you want to say
Maybe
something.
maybe I was just checking that I was really mute.
Ah, okay. Okay, so I'm watching who is unmuting. Okay, so be careful. Yeah, I saw you, Fernanda. Alejandro. Okay. But if you want to say that, I mean, you can keep it on mute. It's totally fine. Okay. But anyway, I don't know. Is any other question? No one is there to unmute.
Well, yes. It is supposed that this kind of algorithm is more in the client side, right? It's not like in the cloud per se, because they are trying to avoid to getting like a bad use of the cloud. That's what I think, because in the diagram that was presented, most of the architecture was in the PaaS part, and it is supposed that this is just for SaaS, right? We are trying to make for SaaS. So if we want to do this, it is supposed that this algorithm need to be implemented in the PaaS, right? That's my question. I don't really know, because I got what is the architecture and I got what the algorithm can do, but I'm at least for me, it's not like very clear where it's going to be implemented.
Any response, Christian?
Yeah, I think some part will be required on the client side, but for some security reasons, at the end of the day, some strong part will be required to be on the server to avoid any modification.
Okay.
I mean, also in this use case, they're different because they have like this hybrid solution, right? They have both a private cloud, I mean, their own infrastructure. Well, it's not private cloud. They have their own like mail, and on the other end, they also are using the server, I mean, a cloud provider. But yeah, I mean, I guess at the end, you could have fit all the solution in any of both environments. However, it is better to have it on the cloud because of the infinite resource theory, right? I mean, in your end, you can have it, but you will always have limits. And on the cloud, supposedly you have any amount of resources that you want.
Yeah, but we're avoiding that part. We don't want to have like infinite resources, right? We want to get just the resources that we really need.
Yeah, that's the thing. But however, on your end, you would need, I mean, on your bare metal, you would need to find like a way to scale to zero, right? I mean, because even in your end, when you scale to zero, I mean, if you do have your server, if you scale to zero, you still have to pay for the server. So even having a limited or fixed amount of resources on bare metal or physically is not like that great. So, I mean, it's like this kind of trade-off. You do have this power to have all the resources that you want, but just take a lot of care with it whenever you're on the cloud.
Oh yeah, well, maybe this was the thing that was not clear at all.
Yeah, I mean, they really don't. I mean, listen to the paper, they don't really go like that much into, hey, why do you have like this solution? I guess they just said, this is how it looks like. Don't ask about it. I mean,
Yeah, kind of. Yeah, because at the end, if you see when they are like doing this use case in the dengue study, they are just like applying. They are talking like about four parts or step of the full architecture, and they are just like implementing just one, right? They are not like using all the other ones. Well, at least it seems like that.
do you mean like the steps of the algorithm?
No, they say that the architecture is like 4 steps. You see the diagram in the PAS. They
Yeah.
have like this scheduler, the security, and all that kind of stuff. But for the dengue study, it seems like they are just using one of them and not the 4 of them.
Yeah, they don't talk like at all about the security and attack detection, for example, or
Yeah.
I mean, they don't even go and say, I am using this dynamic resource provision. I mean, I guess their example mostly focuses on like the scheduler,
Yeah.
which says at first, right? Like just initialize everything, be very greedy, and then after being very greedy, just start like adjusting little by little. But again, I mean, this is what they really focus on. They don't go into like the other layers of the architecture.
Yeah, it's a digestive version of all the full proposal.
Yeah, it's like the diet version, right? Like the one that no one likes. I mean,
Yeah.
Okay, thank you, Christian, and everyone for participating, presenting. We can have 5 minutes break. We come back by 7:35 and we continue with the second paper. Okay.
Okay. Thank you.
So the second presenter is Manuel.
Yeah, sure.
Go ahead,
Let
you can
me-
share your screen.
Yeah, sure. Can you see it?
Yes.
Okay, perfect. Well, I'm going to talk about the failure management for reliable cloud computing and taxonomy model and future direction paper. The main idea in the paper is to propose a comprehensive path of failure management in cloud computing, and they are going to talk about the taxonomy. So the taxonomy is used to investigate the existing techniques that are using in the academic and industry groups in order to work with the reliability in cloud computing. So, well, right now there is a lot of people using the different providers. The principal ones are GCP with Google, AWS with Amazon, and Azure with Microsoft. And since there's a lot of people using this kind of services, also there are a lot of different failures and problems with the SLAs, data corruption, and job loss. So the idea in this paper is to identify the principal problems in the current generation of cloud providers, services. And with this, we can propose the workarounds for the problems for the next generation of clouds. Okay. So now reliable cloud computing is the ability of a cloud computing system to perform the desired task or provide a required service for a stay time period under predefined conditions. Well, in the paper, they talk about different approaches to reach this kind of reliable services. I'm going to talk about the benefits of some of them. The first one is the RRM, and well, it's effective in providing reliability and fault tolerance against malicious attacks and failures. The next one is ARM. Well, this is really nice because you can reduce the underutilization of your resources and you can enable the parallel negotiation with many resources. So I feel like this is like a really it's a really good idea because like a lot of times you have a lot of resources that you are not using and they are just there. So in this way you can work with this kind of problem. Now the ESRAM, here we are going to use multiple state backups in order to work with this kind of problems where we can lose some nodes. So we can use the backup of the state in order to recreate like the system workflow. In this way we can work with a better latency and throughput in the whole system. And finally, talking about the DCLTA, it's a base fault management technique. And here we are going to schedule tasks on cloud resources for the execution, and we are going to focus we are going to try to reduce the faults in the task that we want to execute. So, okay, in the taxonomy part, we are going to talk about different topics. The first one is the design principle, and here we are going to talk about three principal subjects. The first one is the recoverability. In this part, we want to be able to recover a system, but without a lot of involvement of a human being. The next one is the data integrity. So this part, it's really important because you can have a really reliable cloud service, but if you can be sure about the accuracy and consistency of your data when you recover some kind of processor or something like that, it will be useful to have this recoverability. And finally, about the resilience, we are going to enhance our systems in order to reduce the effect of some failures in the workflows when we receive some kind of interruptions in the cloud service. Also talking about the quality of service, there are three different parameters that we want to measure and be aware of them. The first one is the service availability. And here we are going to use the service uptime and also the service downtime. In this way, we can obtain the metric. Also, we are going to use the resource utilization. And here, well, as you can see, we are going to use the actual time spent by a resource to execute workloads and the total uptime of our resource. And this way we can obtain like the amount of resource utilization that we have in our solution and the security part. Okay, the next one. Well, there are these four types of architecture. The first one is a homogeneous one, where we are going to have this kind of same configuration for all the different resources. And well, the heterogeneous is like the opposite. And also the centralized one, where we are going to have this kind of central controller or node in order to manage all the different tasks or requests that we are going to receive from the user. And the decentralized one, where, well, and they are going to work independently. So they are going to know which kind of task they need to execute, and they are going to share their status or the job that they need to do. Okay, so there are some, well, talking about the application management, there are 5 types of application. So the first one is the web application, where we are going to have it up all the time. The streaming applications, where we are going to download the required components. The compute intensive, where we want to finish the workload to comply with this kind of deadlines. Data intensive, well, we are going to deal with a lot of data and their transformations. And the scientific workflow, where we are going to simulate some real world scenarios. And well, there are 2 principal types of mechanisms, the proactive and reactive. Well, the first one, we are going to monitoring our resources, and if there is any problem, we are going to handle with it. And the proactive, here we are going to work with some kind of predictions, and we are going to use like the past information about the previous executions in order to create this kind of predictive approach. And okay, there are different protocols that we are going to use in order to be sure that we are going to handle the different problems that we can have in our solution. There is like this kind of checkpointing, where we are going to create a snapshot of the state of the system, a replication where we want to share information through our cluster or nodes. The logging one, where we are going to store like a lot of important information. And the VM migration, well, we want to move some VMs from one cloud data center to other. And there are different technologies that we use like all the time, and they use this kind of different protocols, architectures, mechanisms, and that kind of stuff. Here, I'm going to share with you this kind of table where we can see the technologies and the protocol that some of them use, the mechanisms, the architecture, and yeah. I feel like the most famous ones are the Zookeeper and Kafka, Hadoop, Spark. Well, in the next slide, I'm going to talk about some of them and how they deal with the fault-tolerant mechanism. Okay, the first one is Spark. It's one of the most famous, and well, it provides APIs to work with it with Java, Scala, R, and Python. And here we are going to work with this kind of workflows using streaming data or batch data, using in a memory approach. The type of service, we are going to build applications that exploit machine learning models, data transformations, and graph analytics. And how Spark deals with fault tolerance. Well, Spark uses a resilient distributed data set, RDD, and we are going to use it in order to replicate the different data sets or data frames or the data through the executors in our cluster. And also we are going to use a checkpoint. So if there is any problem with some of the nodes, we can recreate the RDD with the checkpoints, because it's something like the history in the different transformations that we create in order to obtain some desired data. Okay, now talking about Kafka. Well, we are going to use Kafka in order to build real-time pipelines and streaming applications. The type of service, it's a distributed stamp store, event store, and stream processing. We can use some technologies such as Flink, Spark, Beam in order to work with these kind of events. But also we can use stream processing in Kafka in order to create some kind of aggregations or something like that with the data. And after that, we can store it in any kind of sink like a bucket or some database or something like that. And the way that Kafka deals with the fault tolerance mechanisms, They are well in Kafka. We are going to work with replicas. So we are going to have some kind of data, and we are going to create the replicas of that data in the different nodes or brokers in the cluster. So in this way, if there is any kind of problem with one of the nodes, we can use the backup, and we can recreate that data from the different replicas. So well, it's really useful. Well, now talking about Flink, actually I don't have a lot of experience with Flink, but I know that there is some benefits and differences with Spark. And principally talking about the streaming data, here in Flink, we are going to use some different window wins solution. And we are going to use windows in order to know how we are going to deal with data that arrives late in our Flink. So yeah, actually I don't have a lot of experience with Flink. Well, we are going to perform data analytics and machine learning, and the way that Flink works with the fault tolerance mechanisms. It's that they are going to create this kind of consistent snapshots of the state of the cluster. And the different nodes in the cluster, they need to know each other in order to create the snapshot of the whole system. And finally, with Apache Beam, well, here we are going to define and execute data processing workflow. We can work with streaming data and batch data. The type of service, well, we are going to analyze data stream to solve real-world challenges of stream processing and also batch. So yeah, and about the fault tolerance mechanisms. Well, in the paper they mentioned that Apache Beam use some kind of login. Actually, I didn't know about it. I think that they, as far as I know, in GCP they use a bucket, and in the bucket they are going to store like this kind of checkpointing, and in that way, if there is any kind of problem, they can consume the checkpoint and recreate the whole workflow. But well, in the paper they mentioned that they use a login. Okay, so now I'm going to talk about a conceptual model for reliable cloud service that they mentioned also in the paper. And well, we are going to have the different layers. The first one is the cloud users. So here we are going to have some users that submits their request, and they are going to expect to obtain some kind of SLAs. Okay, after that, the workload manager is going to be deployed in order to handle the different incoming user workloads. And then we are going to deal with the next layer. The middleware is like the most important one. And we are going to have 5 different subcomponents. The first one, the accounting and billing, in order to understand our expenses. The workload manager, in order to reach our quality of service for every workload. The resource provisioner. Here we are going to have 3 different components: the SLA manager, VM manager, and fault manager. And also we are going to have a resource monitor and security manager in order to deal with the security policies that we define in our solution. And finally, there is a physical infrastructure layer, and well, it's the data centers with multiple resources. We are going to have some kind of resources like processors, network cards, storage devices, and disk drives. And we are going to use these kind of resources in order to execute the workloads in the cloud. Talking about when a cloud computing system fails, they talk about some different reasons about that, and the principal one is the hardware failure. It's like the principal of all of them. So yeah, in the paper they mention a few research directions in order to talk about some important topics. The first one is energy. Here we want to provide a reliable cloud service, and it's required to identify that how the occurrences of failures affect the energy efficiency of cloud computing system. The security part, where we want to deal with, we want to obtain this kind of traces that can be used to create this kind of empirical or statistical analysis about the different issues in the cloud in order to test the performance in terms of the security of the system. The scalability, the latency, and the data management are also one of the most important. Talking about the data management, there are some kind of overloads or bottlenecks because we are working with data. We want to synchronize the data that is stored like in different places, and this kind of approach cause overloads in the cloud service. And well, actually that's it. I don't know if there is any question.
Okay, I think we can move to the discussion to talk about the 3 questions. But before that, does anyone has any question about the presentation or something? No. Okay. We're going to main focus the 3 discussion questions to the failures, the reliability tools, and the future challenges. So the first question that I have for you is, why do you think resource failures have more percentage of occurrence against the other ones? Because we have here the 58%, but why do you think it can be a problem right there?
Depending how you count the failures, right? Because also if one hardware has like a failure and the entire hardware fails and it's providing some service to several websites and things like that, do you count it like one failure or several failures?
Yes. Well, basically, from my my thinking, I think this is related with the usage of hardware. You know, in data centers, we have multiple hardware devices, such as peripherals, memory, CPUs, and so on. So as you said, if one piece of hardware fails, maybe it can destroy all the system in that case. So I think because of hardware is more tangible than software, the percentage of occurrence of failures can be more as expected, but I don't know. What do you think about that?
The percentage of the occurrence is about the time. Okay, so that's like, it means 58% of the time you would experience failure in the system. That totally makes sense. I mean, it doesn't mean the whole system fails. You would explain some sort of memory failure, some sort of RAID controller, disk drive failure, power outage, basically failure related to power, related to circuits, related to memory. So it means 58% of the time you would, I mean, at least I understand it like that. You will experience some sort of hardware failure. And that totally, to me, makes sense that you would see much more hardware failure compared to the software failure.
Okay.
I mean,
mean,
just
go
a
ahead.
question there. So do you mean like whenever, for any reason, if I'm doing something in the cloud and it fails, 58% of the times is because their hardware failed? Do you mean that? I mean,
I don't know. I mean, you should have that. There is one like that 1, 2, 3, 4 is basically references about that percentage of occurrence of failure. I would like to see like what exactly how they define that. But you remember in the distributed system course we were discussing, even if you have a system, I mean, uptime of the system and hardware is like 99.999%. Okay, that 0.001%. And if you have downtime for that particular hardware, and if you have tens of thousands of system, you would most of the time experiencing failure. It doesn't mean the whole system, but there is one failure in one part of your cloud infrastructure.
yeah, I see.
I mean,
So,
there is something going on most of the time.
and the other question was just for Alex for a second there. I mean, now you're I know you're a lot in data centers and really like testing hardware and stuff. Do you really get into some scenarios in which the failure can be attributed to a complex circuit design?
Yes.
And really, I mean, up to the point on which you are already like testing stuff, you just, hey, this circuit keeps failing. I mean, those type of errors really get all the way up to you?
I mean, by the circuit by itself, no, not all time. Or I mean, I have never seen that before. But the failures that I have been involved are not only about well, it's most of the time about the CPU and memory, BMC and all that stuff, because of the complex circuit design is almost the same. They recycle that type of circuits year by year. So yes, it's more about the components, because not all time all the components are in the same fit, because I don't know, there are multiple semiconductor providers as Intel, Micron, NVIDIA, and all these platforms are like a Frankenstein of different components. So you can never trust of the vendor.
Yeah, you're right. Okay, I see. Thanks.
Okay.
One comment.
Yep.
So also on the hardware failures that they said like 50% of the time it fails, but well, that's also among all the existing hardware, right? And software, probably there are more options of software. How would you quantify the things? Because it's like, yeah, the accidents from cars and airplanes. So there are like less airplanes than cars, right? If one accident by car happens, it provides less percentage than if an accident of, how you say, of an airplane happens, right?
Yes.
So I think that also matters a lot, right?
Yes. I have a discussion also with, as you say, in a plane. There was an, I don't know, it was in the newspaper in the US that a plane failed because of the embedded system that they have. Well, this is not about cloud, I mean, but it was about hardware. So yes.
So what's the name? The rocket, like long time ago, right? Because of the operations. That one of the operations, the ALU, I think, it's how do you say? It didn't carry some values, and the operation got wrong, and the rocket exploded. I think, from the NASA, long time ago. I don't remember when, but I think that people remember that, right? Even when probably, I don't know when happened, honestly.
I didn't know.
I know about a real case that I worked on, that a customer used an Intel server, and they also developed through another vendor an Ethernet PCIe card, but customized for their model usage. But due to the complexity of this card, didn't comply the basics like requirements for the or was not well validated for the Intel server. But this is a complex design and complex systems. The vendor said that Intel has the fault, and Intel said that we were fine, and the vendor was doing the wrong way. And this is how the complex design of the circuits could also be a cause of failure in cloud computing.
Okay, I didn't know that. Also, nice. Okay, so I will move to the next question. In the next question, it's an open question because I want to hear about your experience. I know that most of you have had some experience in the technologies that I will mention. So have you ever used any of the tools mentioned in the reliability techniques, or either in the application type or a protocol, like Hadoop, Spark, Kafka, Zookeeper, Cassandra, etc.? And if you have heard about the open issues that are right there, I can make an example. I used Hadoop before, so I know that this technique consider only homogeneous workloads. I have used that for MapReduce, but I don't know. What do you think about all the technologies that are mentioned right there? Have you ever had some experience? This is only to get like the add value for the questions, to know about your experience.
I didn't understand exactly the question. I'm sorry.
If you have you noticed something about the open issues, or share your experience about the architecture of these technologies? Protocols or
But
something
only
from
from these ones?
Yes. Are they related to the paper? I don't know, Paul.
Yeah, from these ones. No, that's why I was asking you from these ones.
Or from another ones? I don't know.
Well, we
Yeah.
have Cassandra there. Cassandra is the database.
Yes.
Yeah. But what's like, are you aware of, like, have you faced any issues? That's my understanding, right, of the question. You have,
Yeah, from the right side, the open issues, right? Yep. If you have heard about for example, Cassandra, the resource utilization concierge. I don't know.
And just to clarify this this table a little bit, basically this table is representing those papers that are cited by the authors, okay? And those authors, basically, they suggested certain techniques in order to basically, I think, in order to improve certain certain factors in quality of service. And the technology that they adopted is those things. And the open issues are, I assume, is the open issues in the paper, not necessarily in the technology. I'm saying not necessarily because I don't really work with them to realize if that open issue is really persist in that, for example, technology or not. So the author might refer to that problem in the paper, not in the technology.
Okay. I think this was a really hard question because I don't know. We don't have a lot of experience on that type of technology. So let me move for the next question, maybe. Okay. Can you go to the slide of the future challenges, Manuel? Among the future challenges that we have right there, which one do you consider is the most important that we need to focus, I don't know, for research directions. I mean, on energy, on these systems, the exascale systems, we know that we have a trade-off between power consumption as the cost of resilience. And I have heard a lot of people talking about energy in terms of power consumption. And I don't know, what do you think about to solving like those problems?
I don't know. It's a really hard question. I mean, which one has more importance to?
For you, it's like I mean, like, from a subjective point of view, nor from an objective
Because
point of view.
if you,
from-
if you see
from-
it in a, like money wise, like if you see it environmental wise, if you see it like I don't
Yeah,
know.
at the end of the time, I think it depends on what you are looking for in your application or in your use case, right?
Mhm.
If you want to
Exactly.
like point in to the energy, well, for you it's going to be the more important. But if you want to have like this amazing performance, but latency is going to be like the major issue for you.
I mean, for the one that I at least in the system that I have worked with have really seen it being affected by fault tolerance, or maybe being unable to handle fault tolerance, has been security. I mean, once in a system I was working at that was very related to a bank, I mean, when starting, we didn't set up like all the checkpoints to it being restored from a given point, and we have a failure, and we have like a missing gap in our time. And whenever we were audited, we were like having a lot of problems because of this missing gap of time, because numbers didn't match at the end. And yeah, I mean, I see these kind of like systems like Spark, Kafka, Flink, and Beam that do have like a ton of already, like they are already using techniques to guarantee this fault consistency. But it also depends a lot on you being able to use it correctly, right? Because it doesn't matter at the end if I just use Spark, but I decide to only set it in a same geographical region, right?
Mhm.
I mean, because if that region fails, then whatever Spark had it working, it doesn't matter, right? I mean, so it's not only the technology, it is also you taking decisions and taking into account that this technology will help you, but first you need to really take into account how to help that technology excel.
True. Yeah. I mean, from my perspective, I mean, energy, data management, scalability are more like, how can I say, financial issues. I mean, if you spend money, you would resolve those issues without much problem, okay? But security, as Rodrigo said, I think has the highest impact. I mean, if it goes wrong, and it's not that if you spend more money, you can really make it more secure. Because it doesn't go just equal, right? Okay, I spend more resource, I make it more secure. It doesn't work like that. And for the latency, we can improve it to a certain extent by, again, by money, I assume. I mean, the more you have distribute your servers and data centers all over the world and replicate the data, you can reduce latency to some extent. But again, there would be some, I assume, technological limits that where we cannot pass it anymore, you know, at least currently. So I would say the one that is more critical is security, and maybe the one that would be harder to deal with, I mean, to bypass that theoretical limit would be latency.
Yeah, for latency is very interesting. I mean, we had also this scenario in which we were spending more to have less latency, but at the same time, it was more prone to failures, because since we were keeping everything cached, as in memory, not really at disk. I mean, to have faster reads, even though, I mean, they were consistent, of course, but whenever the system would reset, we lost the information because we didn't set like a just drop it into the disk every so often, because that takes more time, even though it brings up more. Again, it's a very interesting research direction because of this, right? Because even wasting more money, I mean, investing more money into having less latency doesn't necessarily translate into being less fault tolerant. So
Okay.
Yeah, that's true. Anyone else, you want to add something? You want to share your
I
perspective?
have a question,
Right.
Madi, about security. As you said, it doesn't work about money, but which is the factor it depends on security.
But it's like a business, right? He said that it's not like directly proportional, or there is not like a
Yep.
formula. You can spend a little money and have ultra good system, secure system, or you can research and spend a lot of money and have like a specialty security system. It's like companies, right? That like, let's say you can invest a few and gain millions, or you can invest a lot and lose all the money because it didn't succeed. No, it's like an analogy, more or less
Yeah,
similar.
exactly. I totally agree with Paul. It's not proportional. I mean, you spend X, you get one level of security. You spend 2X, you get 2. You spend 10X, you get 10 times better security level. It doesn't work like that. And I think it would be really hard to get it totally right or near total right. It would be really, really hard. And again, as for example, in the case of Rodrigo experience, it's really hard to get it right. And when if it goes wrong, it can be really drastic. The effect can be really drastic. It's not about now. I don't know. Should I deal with like a 2, 3, 10 nanosecond more latency? But then, I mean, the effect can be really life-changing, basically, if that one goes wrong, particularly. And it's, I think this one especially requires more important research because, again, I don't know if you proportionally research, you may not proportionally increase the security because a certain part of it would be again related to human being as the whole, right? That it's hard to have them, to train them correctly, to inform them correctly. So I don't know. I mean, all those things I combine, I think security is the hardest one to get right among these things.
Interesting. Okay. Thank you, Madi. Thank you, Paul.
Anyone have any other feedback, comments, idea? Okay, so perfect. Okay, thank you, Manuel. Thank you, Javier, and everyone else to participate. So we can have now like another 5 minutes break. So we come back 8:20 and we continue with Ricardo Rey as the last presenter. So 8:20. Okay, just stretch yourself and come back. Okay, guys, if you're back, please keep your camera on, or if it's possible. So you can go ahead, Ricardo, you can share your screen and
Sure.
start your presentation.
Can you see this presentation?
Yes, yes.
Okay, cool. Yeah, so I'm gonna talk about cloud computing service composition. I'm sorry in advance, the paper was a little bit dry. I think that pretty much all of these literature review papers are kind of dry. And my PowerPoint or whatever slide making skills are the worst you will ever see. So I also apologize in advance for that. Yeah, so let's get started. So we're gonna talk, the paper discusses cloud computing system composition. So basically it starts off by describing what the hell is cloud. So yeah, so we can get started there, right? Like do a quick recap of what we mean by cloud and what it is, right? So we will use NIST's definition. So it's essentially a model for enabling access to a shared pool of resources. It's usually through the internet. It has 5 characteristics, 3 service models, and 4 deployment models. So the 5 characteristics, we kind of already know them by now, but in a nutshell, it's on-demand self-service. Like you don't have to ask someone to deploy infrastructure for you. You just like call some APIs and you get them. And also, this is part of the pay-as-you-go model, right? So on-demand self-service. Broad network access. The cloud is typically accessible around the world. Like for instance, Amazon, it doesn't really matter where you're at. They have data centers near you and you can use their public cloud. Resource pooling. Resources are essentially transparent to users. You ask for blah and Amazon makes it happen, right? Or whatever, the cloud provider makes it happen. They do this by having a bunch of machines that they cluster together and they speak to each other. And in the end, you can see them as kind of like a cohesive, unified resource. But in the end, it's like a bunch of machines lying around there somewhere. And it's part of the cloud magic that makes them look like a single resource, right? Or like the subset of hardware that you requested. Rapid elasticity is another of the characteristics. Elasticity is basically related to scaling fast. So it's scaling up or down fast as required by demand. So for instance, if you have 3 containers or 3 servers serving web requests, and you have a fire sale, and now you have like 10 times more traffic than before, a good cloud should like pretty much immediately spin up some more servers for your traffic to be balanced correctly and for your like QoS to be achieved. And finally, the service is measured in the sense that whatever, like every API call you make, it's counted. Every time you use the storage, like queries are counted. Like every time you store something, you query something, it's counted. The CPU time that you use, the memory usage, everything is controlled, monitored, optimized, and reported. And this ties back to the pay-as-you-go model, right? So for instance, with Lambdas, which we have discussed before, if no one calls your Lambda, then you don't really pay for it. And like if you have something that is really storage intensive, then you're going to pay a lot. But it depends on usage. So NIST's definition doesn't consider 2 other definitions that do show up in some of the literature. Multi-tenancy, essentially, it is entirely like, it is very possible, very likely, that the hardware you're using is not for your own personal usage. It is very possible that other companies, other people are using it, and the cloud needs to support this in the sense that it's good for them, like the providers support this because it's good for their business. Like they want to utilize machines as much as they can. And for you as a user, it has to be transparent, right? Like you have to see it as though it's your own machine. And this has some security implications on their side. Like they need to make sure that the fact that your software and my software live in the same machine, we do not like step on each other's toes. So multi-tenancy is an important part of the cloud, which is not part of the initial definition of NIST. and auditability and certifiability, which is logging, right? Like in AWS, we have CloudWatch. So pretty much everything that happens is logged, and it's kind of good for debugging. I actually hate AWS logs, but yeah, they are there. So they provide some audit and certification capabilities. So those are the 5 characteristics. Just recap here, nothing new. The service models are the star AAS things that we know already. So there is SaaS, PaaS, and IaaS. So basically, service as a service is the software as a service is the higher level of the stack. Wait, actually, give me a second. I think I'm getting confused. No, yeah, this is the right slide. Sorry. So when they give you software as a service, it's essentially the top level of the stack. You don't manage pretty much anything, and they just give you everything, right? Let me see. Yeah, here it is. Actually, these are some definitions. I'm getting ahead of myself. So yeah, let's define something. Service is a mechanism that is capable of providing one or more functionalities. So that's like a very hand-wavy definition, but when we talk as a service, it's something that does something for you, right? Like, I don't know, Amazon is a e-commerce service. A platform is a computer system which includes hardware, OS, and optionally some developer tools. And infrastructure is the underlying physical hardware. So this typically includes processors, storage, networking equipment, etc. So with these definitions in hand, we can define the 3 models. So we have the lowest level in the stack is infrastructure as a service. Basically, this is the most bare bones they can give you. And the vendor gives you compute, storage, networking, virtualization, and you're responsible for everything, like creating the VMs, the containers, installing the operating systems, patching them, like making sure everything's running smoothly. It's all on you. Like they just give you the hardware, basically. Platform as a service is a step above. They already give you things like the operating system, so some middleware such as databases. So typically at this point, you kind of use one of these when you want to care about the application and the data, and not so much about the management of the underlying hardware. And finally, you have software as a service, which is the top level of the stack. Basically, some company gives you a piece of software that is already like done and dusted. You don't have to do anything. You're basically a user of these service. So examples are like Gmail or Google Docs, right? Like you don't have to actually do anything. You just use them, right? So this is software as a service. So those are the three service models. And then we have the 4 deployment models, which is like a public cloud, for instance, like AWS, private clouds, like the ones we discussed a couple of weeks ago that you can build with OpenStack. A community cloud is essentially a private cloud, but shared by multiple organizations. So it's like they can use it. The definition kind of seems redundant with private because it's private to those companies, but the paper does mention it. And then hybrid is some combination of the above 3. So now that we know what's the cloud, and well, rather now that we recapped what's the cloud, we could talk about system composition. And system composition is essentially building a complex system out of simple systems, simple atomic services that are the building blocks, right? So cloud computing system composition refers to a process of doing system composition with all the options that you can find with cloud vendors, and doing this in your cloud kind of environment, right? So I honestly looked for a lot of examples. Like I wanted to get a real sense of what the hell this system composition is about, and I could not find anything. Like I looked like crazy because the whole concept sounds like very abstract to me. I couldn't actually find it, but my intuition is that, for instance, maybe you can put your service in AWS, but you don't like DynamoDB, so you use some other cloud providers storage, right? And maybe like you don't like how Route 53 does DNS, so maybe there is some third party, like maybe not AWS, not Google, some other service in the internet provides DNS capabilities. So I think that's what it's talking about, right? Like you don't have to build everything yourself. There's a lot of services that kind of like work out of the box. And the problem is, how can you decide between all these services to build your complex service in the most optimal way? So the idea is that system composition is so hard, and the paper mentions that it's an NP hard problem. It cannot be done by hand, or it should not be done by hand. So basically these algorithms consider variables such as the quality of system of the simpler systems, service dependency conflict, security, etc., in order for some algorithm or source or some system to select the best services for your application. And it boils down to an optimization problem. Just as we've seen before with cloud scheduling, which is essentially like how do we optimize the resources that we have to run this application. This is yet another example of an optimization problem, right? Like we are looking for the optimal set of small, simpler systems that will result in the best like complex compound system that we're looking for. So there are 5 categories for like in the paper they identified in this literature. I believe they read 34 papers. There are essentially 5 categories for how the different authors that they studied attack this problem. Basically, there's classic and graph-based algorithms. There are some combinatorial algorithms, machine-based approach, structures, and frameworks. So the most common attack vector for this problem that they found in the literature was classic and graph-based algorithms. So by classic, we mean things like backtracking or the knapsack problem. We probably all know them, but backtracking is like you look for a bunch of options, and eventually like you like step back a couple steps, and then you look in another direction. So it's like a very thorough search of your search space, but it's like it results in exponential time execution. The knapsack problem is the one we all study when we're learning dynamic programming, which I don't know anyone that actually knows dynamic programming, but everyone knows the knapsack problem. It's the one about you have this bag with so many items, so much capability, and these items, and each item has like a importance factor and some weight. So how can you maximize the benefit with respect to the capacity that you have? So some people, some of the authors that were studied in the literature attack this problem as a knapsack problem, right? Like how do I use all these services in the best way so as to optimize the complex application? There's another algorithm mentioned, and by the way, again, this paper was a literature review. So I'm essentially just like enumerating some of the options mentioned in the paper, and I didn't honestly go deeply into all of them. I looked around into a couple of them, but this is me just like kind of enumerating them and just a little bit of extra research. So in the paper, they mentioned this SMA algorithm. So if this is a graph algorithm, they calculate like they considered the nodes are inputs, like one edge is like an output and the other for one node, and it's the input for another, right? So they calculate the degree to which the outputs of a service can be supplied as inputs to another service. So like let's say maybe Route 53 outputs the domain names in some specific way. I mean, I highly doubt it, but just for the sake of for the example. So maybe if the way they output like the DNS mappings is very like specific to Amazon, it cannot be used with any other system that consumes them, right? So this thing calculates the degree to which the outputs of one system can be used as the inputs of a different one, so as to be able to figure out all the different combinations, and then from that they can follow the path in the graph that maximizes some value, right? Which that value is also something that I think I will mention later. There are some multi-layer algorithms. So for instance, this Liu et al. Proposed one of these. The first layer deals with service selection. Then there's a second layer that once these services are selected, they can like classify them by how stable and secure they are. And then they talk about the QoS parameters. And these QoS parameters are pretty important, and they are not explicitly mentioned until like the half of the paper. But part of the problem of service composition is that QoS, like maybe it's easy to qualify, but hard to quantify. Like for instance, let's say I want reliable networking. Okay, what does that mean? Like maybe are you talking about like sub-microsecond latency, or are you talking about like 99.9999% of uptime? Like what the hell is a reliable network? So some of these QoS parameters are easily qualifiable, but hard to quantify. And what's worse, given n services, the only way you can actually tell some of these QoS like values, like the quantitative values of these QoS parameters, is by actually calling the service and measuring. But sometimes this is not feasible. Like maybe calling the service is not free, right? Like for instance, in Amazon, each time you call like S3, like every read and every write costs, right? Like they charge you per read and write, or maybe by a batch of them, but it's not free. It's not entirely free. And even if it were, maybe you have like way too many service options, like between like the different layers of your application. Maybe there's like an exponential growth of how many services you would eventually need to call. So it's not feasible to just call them all live to figure out at that point in time the QoS of a system. So some people came up with this Cloud Rank algorithm that predicts the QoS of services. So I honestly don't remember exactly how they do it, but they instead of using the real QoS, they predict them. So they're getting into this like heuristic slash not completely accurate, but close enough kind of realm, which is something of a theme when talking about these optimization problems, right? Because sometimes you cannot find the optimal solution. So you find things that are good enough. So these are some classic and graph-based algorithms. There were many more, but these are the ones that I kind of selected. Then combinatorial algorithms, I feel like the paper did not do a good job at explaining what the hell they are. So I looked around and I found some definition that a combinatorial algorithm essentially deals with a system of discrete objects that need to be arranged or selected in a way that minimizes some cost function. So in this case, the system of discrete objects are all the simple atomic systems that will be arranged or selected in a specific way so as to make the compound service as optimal as possible and following the QoS parameters as closely as possible. So these algorithms typically deal with very large search spaces and usually deal with like good enough results. So for instance, some examples that were mentioned in the paper are separating network and non-network QoS services because of like this exponential growth and kind of analyzing them separately. Genetic algorithms where the QoS is a fitness value. There are some algorithms based on game theory, Markov decision process, etc. And some meta heuristics. Kind of again, this harkens back to the scheduler paper we read a couple weeks ago, right? Where in the literature, some people were using like particle swarm optimization or ant colony optimization to solve these. So particle swarm optimization was also mentioned in this paper. So those are the combinatorial algorithms. Then these machine-based methods, they're based on finite state automatons. There was not a whole lot of this in the paper, but essentially like these guys designed a finite state machine to consider service code relations and legal task invocation order. So maybe like there's like some edge from A to B cannot legally exist in the graph. So like maybe if you build a graph and you're starting your graph analysis, maybe you are considering some of these paths. So these guys were like, okay, let's prune let's prune some of the search space. So you have this finite state machine with legal transitions and some pruning algorithms to help reduce the search space. And in the end, essentially, they just calculate the QoS of every path and they select the highest one, right? So this one seems optimal, but this pruning algorithm, I mean, it doesn't really go deeply into it, but it might be pruning some legal or some like more optimal branches of the search space. So again, kind of like best effort thing. Then some of the papers in the literature were using data structures and they created algorithms based on leveraging the properties of some data structures. So the main example they talk about is using a B tree for indices. So B trees are often used in databases for indexing. Like when you create an index in some database, it's typically stored in a B tree because it has some like good like ordering and iterator kind of properties. So yeah, some databases use B trees. So these guys were like, hey, maybe like we have a lot of information about all the services. Maybe we can store them and kind of like create this database of services and use the properties of this B tree to kind of make searches in the search space more efficient. So for instance, this structure encodes properties such as the service type, the security, quality of service parameters. And they propose a query algorithm for using this B plus tree for fast lookup of what services would match the given criteria. And this method, according to a paper, was shown to be like 100 times faster than brute force search algorithms for cloud computing service composition with around 10,000 service providers. And finally, frameworks. This is the most hand wavy. It's not just the algorithm, but like complete frameworks for solving this problem. So for instance, some of them, some papers proposed agent-based frameworks in which there's an agent that receives requests and provides service management from end to end. Framework for conflict detection policies and user requirements. So essentially, like you give to this agent, I guess in some form of an API of some like description file, some YAML. I honestly don't know. It's not explained in the paper, but you give to this service your kind of like your constraints and your quality of service parameters. And it goes through all of the given services and it's like, okay, there's a conflict with this one doesn't match the policy, etc. And this last one, trust-based frameworks, where the probability of a service executing as expected by the user is evaluated. So some of these services, they advertise as they do something, but maybe they don't do it quite like they do. So they have these trust-based, like how much do you actually trust that this given service will do as advertised and kind of as you expect. So there were like 8 research questions, if I recall correctly, but only like 3 of them were actually addressed in the paper. So the first research question was identifying all the categories that were identified. So these were all the categories. I mean, I don't think there's a whole lot of interesting thing going on here, but user requirement satisfaction. This thing, qualitative to quantitative transformation of QoS parameters, is something that I talked about earlier. Algorithmic improvements, essentially the first section, like how a lot of people are taking classic algorithms and using them to solve this problem. Novel data storage is this thing I just spoke about related to the B plus tree. Self-adaptability, reliability, accuracy. Some set of papers talked about improving and improvised QoS mathematical models. Some of them dealt with revenue maximization, optimization of the service discovery process, and frameworks and structures. So not a whole lot going on here, just like kind of the answer to a research question. Research question 3, data sets and benchmarks used. So basically in here, the authors were kind of like badly surprised that there's not a whole lot of standardization with respect to this question. Different researchers were using different data sets to evaluate the problem. They were using different benchmarking tools. So for instance, in the space of data sets, there were only 3 data sets that were kind of like used by the biggest intersection of researchers. But there is a big lack of data sets to evaluate this problem. So that's a big issue. Like it's hard to analyze how good some algorithm or some approach is doing with respect to service composition. And then the QoS parameters that are accounted for the most, that's RQ6. So basically the biggest quality of service parameter is cost. And I guess this makes sense, right? Like if you're building an application, you typically want to reduce cost. I actually forgot some of these acronyms. I forgot to pull up the paper, but they're there. Availability, reliability, the reputation of the service that you're going to use, the throughput, the latency. So here are all the parameters that were accounted for in all the papers, right? Like obviously none of them were counted in all the papers, but this is the histogram of how many of the papers dealt with some of these parameters. Yeah, and future work is, as I said earlier, there's no standardization in the data sets that was used for the by the researchers. So having some standardized data sets will help a lot in answering the question how good this approach is, right? Because if I have my own data set and my own data set says that my algorithm is a-okay, but if I try this in your data set says that my algorithm sucks, then we have a problem, right? So standardization, the data sets used for evaluating the quality is important. Then there is no good benchmarking environment, right? Like, again, people were doing ad hoc things. So coming up with a consistent framework and environment where every researcher doing like investigation in this space can use it and say, hey, I ran my new algorithm, my new framework, my new whatever against this benchmark that is well established and that we're all using, and it did better than all of the other ones, then that's an important thing to do, and that does not exist right now. And some future work mentioned was also like coming up with new mathematical models for calculating these QoS values, right? So as I mentioned earlier, talking about them qualitatively is relatively easy. Actually quantifying them is a whole different beast. So there's a need for some research in this area. So yeah, thanks for coming to my TED Talk. And if you have any questions, I'll be happy to try to answer them. But yeah, the paper was kind of dry and it just enumerates stuff. So I don't know how much I will be able to answer, but happy to try.
Thank you, Ricardo. Yeah, I totally understand. I mean, survey papers, as you say, they can be dry and they can be hard to explain and present or talked about because they introduce a lot of concepts. And yeah, I totally understand. I hope that it doesn't happen in the next part of the presentation, so you can pick really good, interesting papers. I mean, I hope to see really like some technical papers that you are really interested to, to see.
Yeah, definitely. I mean, I know these kind of papers are important. I actually complained with someone from this class about how much I hated these review papers, and they told me like, well, that's like where you start, right? Like you go to these literature review papers, and they can help you kickstart your own research, right? Like to know
to have a broad view of the literature, but quickly, right?
Yeah, but for this kind of thing, it's just like, let me go through my little laundry list of papers that were discussed. So it's kind of a little bit dry, but hopefully it wasn't too terrible to listen to.
So just a question from me before we go to the actual discussion. So the chart that you show, the pie chart that you show, basically they are discussing how many people are publishing about, for example, these factors, right? How many?
Yeah, my understanding of these graphs is that out of all the papers that they surveyed, how many of them, like different papers attack different QoS parameters, right? So maybe some of them is like, oh, I'm proposing a super novel algorithm to improve the security of the system selected during system composition. So this was essentially how many of the papers out of I believe 34, I think, were dealing with these specific QoS parameters, right? So this is just like, basically, there are at least all of these avenues of exploration when dealing with this problem. And these were just the histogram of how many of these avenues were explored by how many papers.
Yeah, okay, got it. So, I mean, just to clarify, I mean, for everyone, I mean, if we have, for example, more paper talking about cost, it doesn't mean that's the most important problem to solve, okay? I mean, we can't conclude that at this point from number of the paper. Maybe it's just easier to contribute, okay, or to discuss, to understand. That's why maybe there are more papers.
Yeah, definitely. Like for instance, I talked about how the qualitative to quantitative translation was hard. So like cost is pretty much readily available as a quantitative value, right?
Yeah, absolutely.
Whereas things like security, like how do you measure the security of the systems, right? Like maybe you have like a whole gauntlet of attacks that you can try, but there are new attacks coming every day, right? And how do you quantify like, oh, this thing passed 16 out of the 17 attacks, but maybe someone has a gauntlet of 200 attacks. So like, so yeah, probably some of these are the easiest to deal with. So maybe that's why there's more literature about them.
Yeah, absolutely.
Yeah, so, and by the way, the definitions of those parameters are right here. Hopefully, damn it. Let me, I don't know what I'm sharing anymore. Let me stop sharing and open this paper right here. And let me share screen once again and papers to read and share. Yeah, so essentially the little acronyms that were used are coming from here. So for instance, where are you? So RT is essentially response time. So again, very easily measurable, right? So
Right.
so my guess is that the ones that were easier to quantify are the ones getting the most attention, and like things that are harder to quantify, like trust or DC. What the hell is DC? I have seen it before. Yeah, I can't find it right now, but yeah, DC is there. DC. Data control. Yeah, so like data control, that's probably harder to quantify, right? So probably most researchers kind of shied away from going there. Yeah, so that's about it.
Thank you. Paul, you can go ahead. Paul Mejia, you can go ahead and lead the discussion.
Okay. This is this paper was just like particularly challenging in understanding the whole picture of what it is explaining, but I have some questions for you. The first one is let me we have seen like too many things in cloud computing that are heading to an as a service model. We have platform as a service, software as a service, and things like that. What are your thoughts for the future? What do you think that this kind of model will be like as a serviceable? For example, I researched a little bit and I found that this data as a service model that we haven't mentioned in any presentation, I think. What do you think that could be the data as a service is data that you as a company needs to obtain results and also processing of information, huge amounts of data, and you only receive the results without being hurried about the software or what functions are being used. Those kind of things. You only need the data, and this is going a step above that what we know right now, a platform service or software service. This is in my opinion, this is a step above in this as a service level model. What do you think that is the future, or when will this stop? I don't know if I explained myself.
I don't know if you are asking if how many service models we're going to have, like as you mentioned, like data as a service, like software as a service, like platform as a service, like, and I think that actually that's like, at least in my opinion, I think that is going to get are going to exist more and more because people start inventing those names a lot, you know, especially because they want to be super accurate each time. It's like about intelligence. Then they start like, emotional intelligence, this type of intelligence, this, and each time while you do research and you don't know how to explain the distinction between two different type of models, then you start classifying, right? Like probably some of the new service models that are going to exist, probably it's going to be a subset of other approaches, right? At the end. So I think that people are going to start like inventing a lot of names, and then they are going to get popular, and some of them probably are not going to be like real, how you say, official names until a certain amount of people use it. But I think that either way they are going to start increasing a lot.
But this is not this is not inventing names, because you're offering, well, kind of, but you're offering every time more and more as a service models that you are like only getting a product and forgetting about the problems that is on the back end. But I think we will be seeing more as a service things in cloud computing.
Yeah, I guess we'll keep seeing more of those as a service, as long as those prove to be useful for someone else different to the cloud provider itself, like users, right? I mean, because for
nowadays
example,
we have everything as a service.
yeah, I mean, but we don't see, like, for example, why don't we see like RAM as a service? Well, because that is not offered, right? That is not useful. Probably inside of Amazon or inside of Google, they have like CPU as a service or something like that, but they go on and promote stuff like that, right? I mean, it really depends on what really like the market starts needing. I mean, eventually it may happen that, for example, infrastructure as a service gets dropped, and then we would have like something that really external users can really take advantage of. I mean, in some years, maybe it will be like, I mean, right now it is strange. I mean, at least for me, to hear about people that are actually going into data centers. I mean, in a couple of years, whenever you are not into that very big company's world, it will be strange seeing someone going into a server and managing infrastructure, right?
Yeah.
Yeah, and I think, as Rodrigo mentioned, we will be stuck with this service, software as a service, for more time. Probably at the beginning, it will be some kind of specialization from this model, and then it will be like the creation from the bottom for this data as a service.
I have another question. Do you think that in the future, in the near future or middle future, there will be the possibility that you don't need to be like an expert on cloud for doing anything? Like, for example, right now, in the past, I mean, like 10 years ago, it was like you really needed to know a lot about networking for setting a network, right? But now, the wizard, sometimes the wizard in the cloud, or even some, well, for creating a VCM, for example, right now, is just doing some clicks and that's all. They are going to do a lot of things for you. So
Yeah.
it could be the possibility that in the near future, you don't need to be like an expert on cloud for setting like a real architecture for the company.
Most probably. I mean, if you just follow the trend, you see everything is going. I mean, that's a trend in many things. So, I mean, no one can say, no one can see the future, but most probably that's the way to go.
Yeah, and I mean, I don't know exactly how many years ago, like maybe 30, 40, I don't know, like there were no user interfaces, right? Like you had the terminal and the like DOS, and you had to like just run commands, right? And like you even had to install your own operating system in the computer, right? Like, and people were carrying around operating systems in 5.25 inch discs. Now everyone, like, you have the 6-year-olds that can play around with an iPad, right? So technology has improved, and also the user experience has improved. So in that sense, maybe we will get to a point like that, right? Like maybe 30 years ago, what people were asking, hey, do you think that computing will ever be accessible for like just your average Joe? And right now it's like inconceivable for a computer that someone cannot use, right? Like everyone can use a computer because they're intuitive. So maybe eventually someone will figure out how to make cloud resources accessible.
Actually, it happens the same with web pages, right? Like before, only some people could make web pages, and now everybody makes their own landing page. At least that's the first one. I was going to say also the one from the computer, and also about photography. let's say with the applications. Nobody like before, only professional photographers, let's say, could edit pictures and things like that. But now with the cell phones, like even it helps you so much and people are editing like everywhere, right? The pictures. So, and also like, for example, I just posted like from Facebook that now you can generate videos only from texts. And there are other applications that I don't remember the name, where you say like something like, I want you to build me a program of this. And it writes the pseudocode or the code for that in a programming language. You say like, yes, I want a program that prints the numbers from 1 to 10 in C++. And it generates you the code for that. So
that exists, yeah, absolutely. I mean, just a couple of days ago, I saw a flowchart that it was how much you can do with zero coding. Almost you can do anything without even coding nowadays. I mean, of course, it won't be as efficient as coding from scratch, everything, but with zero coding knowledge, just click, drag and drop things. You can do a lot. You can set up the network, you can set up a social network, you can accept payment, you can do everything. So yeah, Pedro, it's going to come apparently.
Yeah, in one of the first places I arrived, they had like a whole stack of mobile apps done with Google Air, no, what it's called? Google what? Google App Sheet. I mean, basically you just like create an Excel sheet and it drops on a mobile application. And then they had like their own database with Airtable, which is seeing your database as an Excel. They connected it like however they could. And that's it. They already had like a backend, a front end, and they didn't have like a single engineer there. And whenever we came in, and because someone from whomever like said we need engineers, and we arrived, they said, why should we invest in you? Since you, yeah, even if you are not giving like value right away, right? I mean, because they said,
why it's expensive.
Yeah. I mean, they were like, whatever we do in the app sheet will bring a value right away, but whatever you do will bring value like in 4 years. So why should I invest in you? And yeah, I didn't stay there for long.
It's true. The future is scary, apparently. I don't know, it's beautiful or scary. You tell me.
Yeah. Well, the second question is, most cloud computing service providers follow the market law of offer and demand. If the providers find the optimized cloud computing service composition, do you think that the prices could decrease? Because as far as I know, the prices for most cloud service providers are based in offer and demand. So if the prices go down, maybe this will open the window to attract more customers in a more planned and organized ecosystem. What do you think about this?
I think that's already happening.
Because
like, for example, service providers are already like trying to like improve their systems, and actually they are lowering the prices because of competition, right?
Yeah, but if you see, actually, a lot of the service providers, they are always talking about money. So they are always like, we have the lower prices, so at the end of the day, we can like the rate between price and efficiency is going to be the better or the best and all that kind of stuff. So yeah, I think right now we are seeing that they are, most of them have the same technologies. One of them have a little bit more, but at the end of the day, well, everything is a business. So the companies are going to try to get the best with the lower price.
I mean, if you mean long term, the prices has no way but to go down. I mean, that's the definite future. I mean, 10 years ago, how much you would pay for 1 terabyte of data? I mean, to store, how much you would pay for certain processing power? I mean, things, I mean, getting cheaper and cheaper, and definitely in the cloud, their services would go down because the cost basis would go down. I mean, if you're seeing long term, I mean, the process would be like that, I mean, for sure it would go down. I mean, in the long term. I mean, each year it should go down because the cost is going lower and lower and lower. For storage, for RAM, for processing power, the network cost, everything.
Have any of you tried AWS spot instances and going into like their how do you say subasta? Like their subasta.
Auction.
But
Thank you.
But
Their-
option, yeah.
Yeah, have you ever like, I mean, have you ever tried like in your works, like saying, okay, I want, basically in the way I understand it, you say, I have this workflow of this size and I will take a spot instance once it gets to this price. And once it gets to this price, you get offered that instance and you can pick it up, do whatever you want, and you return it to the market. And so everyone is already like putting like different prices, which are lower to the price that you should get with an usual EC2 instance. And it's basically an auction market. And if you manage to play well there, you can get like a lot of price discounts at the end of your bidding. I have you. I've never like gone there.
No, that's quite interesting. I mean, not having a fixed price, but letting people basically bidding on it, huh? Bidding, right? Basically, it's interesting.
Yeah, I've never actually used well, I mean, I don't personally use AWS. There's smarter people in my company that actually handle everything related to cloud and Kubernetes and all that junk. But yeah, like what I've seen is that spot instances are kind of like good for batch applications, right? Like if you have like some workload that you do like once per day, and like you don't have to be like super responsive and it takes like a couple hours. Maybe like you can have it run in like 4 hours, but maybe like you want it to run faster. So, but you don't really like, it's not life and death. So you can like actually bid for spot instances. So I think that's kind of like the workload I've seen, but I've personally not used them.
Wow, that's interesting.
90% saving. Oh, that's that's huge discount.
Yeah, it's a lot.
I just copied it from the webpage. I mean, it's stated like that. I mean, if you can try, and if it doesn't fit, we can go on and sue Amazon altogether.
No, that's why they put up to 90%.
You're right.
From 0 to 90%.
Yeah.
No one has quite an
we
internet.
should start measuring, and if it drops like 0.0001 place.
Yeah.
Nice, thank you for these inputs.
Okay.
And
Go ahead.
yeah.
Go ahead. Sure, go
okay,
ahead, Paul.
the third question is, we have seen in QoS quality of service parameters are ranked among too many types of factors such as latency, reliability mechanisms, security, that kind of things that are like service related factors. But do you think that in the quality of service parameters should be included factors, for example, for real world problems like green energy, for example, that could be a factor that should be included in this kind of researches? Because I didn't see anything about this, only like service problems and issues only. And also they talk about energy, but not about this kind of problems outside of this of the service, or another that comes to your mind. I don't know.
Well, about the ones that are in the paper, well, I think already Ricardo said that those are the ones that they found out in the papers that they were researching, right?
Mm-hmm.
So, but about other ones,
apparently the question is raised because apparently that kind of considerations are not being taken. Only like how to say it, like Cloud computing has a big carbon footprint, right? And everything is trending to cloud computing, as we are seeing. But just a few people are concerned about the problems of the real world outside the cloud computing service.
Yeah. I mean, I
And
guess it will happen like it has happened with food, I guess. I mean, it has to evolve in that way, because back in the day, whenever we were getting food, you really didn't care where the food came from, or if the animals were like just exploited, or if it didn't come from animals, right? But then as time has passed, we are now care if cheese is actually cheese, if milk really comes from cows, if cows were treated well, if it is organic or whatever. I mean, but the cloud computing market hasn't evolved into really that part in which we really do care where cloud computing resources come from and what happened for us to get those cloud computing resources. I mean, I do expect it's like also with clothes, right? We didn't care before if it came from, I don't know, like a beaver or something like that. Right now, if someone is wearing like something that it comes from a beaver, they won't be buying it because it says it's destroying nature.
Yeah, it would be nice to see more information about this kind of problems outside of the service that are impacting us in the real world more than a good service, a good SLA or things like that are important for the business, but not for all the people, right? And it has real impact outside of the computer. Just maybe a question for future works at everything that you're doing in your industries. Okay, that's all for my side. I don't know if you have any question.
Anyone has any extra comments, questions? If no, okay. Thank you so much, Ricardo, Paul, and everyone else for participating in the discussion. I made some changes into the Google spreadsheet. Please check it out. And if you want to move your name here and there, please do so. But hopefully, we already have the three per people for the next week. Just please put the papers you are thinking to present and inform me so I can select one, hopefully from 3 that you are suggesting. And if there are some date that you cannot be presented, or you're busy or for so many reasons, traveling, just move your name here and there, but hopefully next week we'll finalize it, okay? That's all from today class. Have a nice evening, everyone. Stay safe.